I'm here to talk to you about Stars Reach, where we are trying to do something very, very ambitious. We are chasing after the dream that we all had when we were 12 of online immersive worlds that felt real. I've been chasing this dream for a really long time. My name is Raph. I was the designer of Ultima Online and of Star Wars Galaxies. I started making my first online worlds when I was a grad student in 1992, and they were made out of just text. And I've been chasing the dream of these living worlds, these alternate realities, ever since. So today I'm going to talk to you about our try at doing it yet again with Stars Reach. Our studio, Playable Worlds, is devoted to the idea that we can make worlds that feel more alive and build stronger communities and really kind of fulfill the potential and build the next generation of massively multiplayer game. Not a small dream, I know, but we're trying. So first, of course, we're going to lead with what is the game? What's Stars Reach at all? And I'm going to give you some insight into how we're doing it. We're doing a bunch of really advanced technology things that are setting on top of Unity in order to pull off the kind of scale and simulation that we're reaching for. So, what is Stars Reach? It is a massively multiplayer sandbox. We like to think of it as a living galaxy. Long ago, an incredibly powerful ancient alien civilization terraformed a whole arm of the galaxy and called it their garden. They had the ability to break open wormholes in the fabric of time and space itself. They had the ability to engineer life. In fact, hate to break it to you, they made us. They made humans, genetically engineered us. We're their pets. They kept us all locked up on individual planets. Not just us humans, also the ones that look like vampires and the ones that look like fairies and the ones that look like, Sasquatches and so on. There's a bunch of interesting kinds of humans out there in the galaxy. But each of us, we're only human after all. We've ruined our homeworlds. Some of our homeworlds are hitting peak oil. Some of them, climate change. Some of them are even in danger of perishing to global pandemics. Highly implausible and yet true. And so it is that the robot servitors of the old ones have allowed us to leave our homeworlds and venture out into the larger galaxy. And it is our task to settle these new worlds, learn to do better than we did with our original planets, and in general, have a blast, because it's a video game after all. That's the galaxy of Stars Reach. And we set out to conquer this living galaxy with a few core design pillars. First of them was we wanted the game to be really accessible because MMOs they've grown ponderous and full of buttons and 20 million HUD elements on screen. And as a result, they've also dwindled in audience because they've gotten confusing and heavy and time-consuming and so on. So we really wanted to make this a new generation of massively multiplayer game, one that was friendly to kids who came up through Roblox and RuneScape and so on. Our second pillar was we want an endlessly explorable, fun galaxy. We want it to be welcoming, not grimdark and doomed the way that so much sci-fi is today, but a place full of rich stories that can accommodate both pathos and humor, and most crucially, that doesn't break the bank when we try to populate it with content. Because as an ongoing service, that's one of the biggest challenges with an MMO is you have to keep delivering fresh content on an ongoing basis. And we have a lot of new technology these days that we didn't before. So we are leveraging high degrees of simulation in the cloud, procedural content, and emergent game design in order to bring really fresh experiences to players. Which meant the third pillar. And that's the one that you should be raising your eyebrow at. Simulating everything. Not building it out of static pieces. Not asking your artists to build the level. And then handing it all over to players. Like, are we crazy? That's a big, tall order there to build the most alive game ever made. But that's what we set out to do. That's what we said, we can give this a shot. We've got enough new technology today. There have been enough new inventions. Compute power is going up. We have the ability to deliver more by thinking in fresh ways about how we build these games. So that's what we set out to do. Everything you saw streamed down on the fly. The environments were entirely generated in real time off of a simulation. Every tree was a monster. Everything you saw is dynamic and can change on thousands of planets in a single connected galaxy. When we say most alive world ever, we mean that on several different levels. The terrain is alive in the sense that all the terrain you saw is the output of a simulation running in the cloud, a cellular automata simulation. And all of the environment is dynamically meshed from the data of that simulation that's coming down over the wire. All of the plants actually run their own independent AI in any other game, they would be one of the enemies. And they grow, and they react to the seasons, and they throw off seedlings, and the forests spread, and the forests catch fire, and they die. And the creatures each run AI akin to the Sims, and even express their emotions in our alien version of sim bubbles over their heads. So when we say alive, we're really trying to push simulation in video games to a degree that can't be done locally on a client device. We're leveraging the power of the cloud in order to really pull this off. And it requires an enormous amount of technical innovation and working closely with our partners at Unity to push the boundaries of what can be done with ECS and DOTS, with our partners at AWS in order to unlock cloud capabilities in order to run simulations at this scale. So, how does it work? Well, I'll tell you. First, let's start with the environment. You've all played with those sand simulators that were popular for a while. Think of doing that. Okay, conceptually what we're doing is cellular automata, Conway's game of life. Only instead of having one entity type that is on or off, every cubic meter of our world knows what materials it is made of, what the temperature is at that location, what its adhesion factor is to neighboring cells. Our little agents are holding hands with their neighbors. And that way, if too many of them stretch out sideways in a ledge, they can give way because the ledge no longer has the tensile strength to stay up. It can only cantilever out so far. And it does that based on the unique physical properties of each individual type of, we call them resources, each of the agent types that exist in the simulation. That's a single static list of them with a whole bunch of parameters. Each one of them knows at what temperature it melts into liquid or conversely freezes back into a solid. Each of them knows what its vapor point is because our water can be heated into steam, float away, and precipitate again down as liquid someplace else. They all have different properties so that if you drop a pile of granite on the ground, you can build a tower out of it. But if you drop a pile of sand, it's going to slump. Right? So that each thing can behave the way one expects it to. We data drive all of this in a giant table so that we can boil it all down to one AI routine that processes all the materials in the same way and leverages only the data. And that way we can avoid writing too many branches in the code and do this processing of this giant grid as fast as we possibly can in order to deliver a good experience to the players. This is only a piece of that grid. It's a really, really large grid. As you can see, we keep just about everything down at the byte level, although we do allow ourselves some very indulgent floats from time to time. Each of these things has its own unique hash ID. They do fall into a tagged tree structure so that we can address, let's say, all the types of soil, of which there's a dozen, as all soil or by individual if we so choose. And then every single cell knows what is in it. And we end up having to create a starter map. Thanks to Unity, of course, we can build custom tooling that enable our designers to build environment rules that make for good playable environments, right? It's really easy to use procedural generation or any other form of generative content to make what AI researchers call endless bowls of oatmeal, right? It's easy to generate oatmeal. It can get very hard to tell bowl 357 apart from bowl 356. So it was really important to us to have a generation system that gave designers control over exactly what the width of the canyons would be so that the combat can be fun, the right amount of flat areas so that players can build their towns on them, the right slopes to the mountains to make for the right degree of navigability, right? All of those things end up under designer control. This graph tool here effectively allows our designer to build an algorithm built out of 1D, 2D, and 3D noise generators. Everything from Perlin noise to simple splat-down circles to more advanced functionality like wave function collapse algorithms. And by stringing these together, they can build, let's say, a landscape of basaltic magma plugs that have congealed into mesas in an environment that still has some hot springs and maybe one active caldera, but the rest of it feels, you know, maybe just subtropical, right? They can specify all of that in advance, and then we can randomize the seeds. And when we need a planet that happens to have a volcanic area like that, we can pull this algorithm, randomize the seeds, pull the algorithms for a couple of other kinds of topographies. Let's say maybe we also want some large glacially sculpted mountains and maybe a desert on that planet. We pull those out of the library as well, blend them all together, and then output a completely unique planet that nonetheless has the playability of the template that our designer created. We do allow the importation of data into this node graph from external tools. We particularly like GeoGen, but it can import from Houdini, Terragen, WorldBuilder, and similar. Of course, it's important that you be able to preview this data. This is not just height field maps. Height fields is kind of a solved problem. We need to output data that is tagged with materials in full 3D, every cubic meter of the entire map data set. So that algorithm library, which you can see in the column there to the left, that generates the different shapes, including 3D noise generators for doing things like carving caves and tunnels underground or weird worm-like protrusions that poke into the sky. We have the ability to place down hint maps so that we can populate the environment with flora. Let's say we want to establish a difficulty curve that goes from one end of the planet to another because we want it to be a dungeon world. Those kinds of things can go in the hint map and allow our designers to shape the landscape via hints that the game server will use when the planet is then generated. The hint maps will conform to the new topography because they are following the instructions of the underlying node graph. And we have the ability to use a number of filters and masks to do things like extrude ledges on the cliffs so it's easier to climb up without running out of stamina, and so on. This map right here, once it's gone through that process, goes up to the cloud and is in the form of just the algorithm description. And it goes to a world generation service that actually generates an individual planet instance. Then that instance is booted into a server, and that map looks like this one. Right there, you can see that weird triangular cave in the background that you saw in the preview. So each cubic meter here, we know the temperature and the humidity. If you look closely, you can see that the dirt that does not have grass on it tends to slump and erode more than the dirt that has grass because the grass roots hold that dirt together. Every one of those materials can then affect player locomotion. It is harder to climb an icy slope than one that is not. It slows you down when you move through the mud versus the dirt. And yes, it might rain and turn the dirt into mud in real time during gameplay. Here you can see us processing that 3D data grid just to diffuse temperature across the map. We actually take the byte range of temperature and map each value in it into a lookup table so that we can compress a wide array of temperatures into just one byte, because after all, we're interested in the temperatures humans care about. We want extreme temperatures to be present in the galaxy, but we don't need anywhere near the level of precision at the extremes than we do in the middle. So we actually take that byte and map it into a lookup table. All of the values that are present in the resource system are used in order to determine cutoff values and behaviors when the simulation works on a given material. The melt point, the boil point, even the angle of repose for that blob of sand that we dropped it ends up sliding until it has a nice dune-like quality to it. How much time did it take to build this? We've been working on this simulation for over 5 years. It has moved through 6 different languages at this point. This is now version 6. It currently runs as a microservice in Rust, and we already know that its ultimate destination is Cloud GPU. And moving it to Rust was a good interim step because it helps us architect towards that GPU destination. The cost of Cloud GPU, of course, has been falling thanks to the AI revolution, and we can run very efficiently on hardware thanks to limiting the amount of branching in the algorithm. It really does lend itself to being treated almost like a compute shader. Currently, we are processing 270 million cells on that map 10 times a second. So you might be wondering, how the heck do you stream that much data down to the client? Even that map then works out at about 60 gigabytes of RAM. And we let the player see most of it, frankly, from where they're standing. So each of the cells is boiled down to only 9 bytes of data, right? We try to be very, very efficient about the cell's data. That also ends up making extremely compressible. We currently serve that data directly to the client, to the terrain renderer, as well as serving it to the Unity server. Both of them then mesh it for different purposes. The server is meshing it to build the collision meshes, and the client, of course, in order to render it. We currently achieve up to 99.4% compression on that data, because as you might imagine, the underground of a granite rock is an awful lot of repeated data, so it compresses extremely well. In fact, this currently works well enough that we actually just send it using HTTP calls, although I can see that UDP is in our future. The cells are just 9 bytes, as mentioned, but we still have to deal with the fact that we have to compress them and decompress them. None of this would be achievable realistically without using burst jobs and dots, right? This is a truly large amount of computation that's happening. We're able to decompress and populate the whole map in just a couple of frames. It doesn't take long at all. Then we have to stack stuff on top of it. Currently, we are aiming at a target of about 20,000 unique objects that can be streamed down on the fly to an individual client when they log into a world. A sandbox MMO like this has to have an extremely high object count, right? Every single one of those trees grew there. They weren't hand-placed. They grow to maturity, they throw off babies, and so on. They go through multiple states. We handle that primarily via rendering on the client by having a smart shader that knows how to adjust and adapt them. And every single one of them is fully scriptable. We could make any one of those trees turn into a carnivorous tree that eats you. At runtime, actually. So every single one of them is a fully dynamic object. In order to pull this off, we had to work really closely with Unity. They've been wonderful partners. We worked very closely with them on updating the capacity, particularly for static object count in ECS physics. Via some optimizations, we've already been able to achieve several multiples of the performance that it originally shipped with. And the gains from that stuff is actually in your hands now because it shipped as part of the recent ECS physics updates you all were able to grab just a couple of weeks ago, which is awesome. We've also worked extensively with Unity on netcode optimizations to achieve this kind of scale. So, one of the advantages to working right on the bleeding edge is Unity likes being right there with you. So if you're working with something like this, you can always reach out to them and say, hey, we're trying to solve this really big problem, and they will help. I mentioned that every single one of those trees was scriptable. One of the beauties of Unity as an engine is that it isn't monolithic. It isn't so tightly coupled that you can't pull it apart and replace pieces of it when you have specialized needs. And we do have specialized needs, right? Like that terrain environment that you saw, we can't use Terrain Engine to do that. Terrain Engine isn't built to handle, voxel-style rendering, that kind of thing. So, that's fine. We can just replace it with our own. The same was true for achieving MMO scalability in terms of dynamic objects and their behaviors. We're a game where there isn't anything static. There really isn't like a handcrafted environment. Everything is dynamic. Everything comes down on the fly. Every single object is capable of having scripts on it. And we actually embed Node.js within Unity Server, and we use TypeScript in order to implement all the game logic. And we even store all of our game data in JSON tables. And we do this for a couple of reasons. One of them is it makes all of the game content hot reloadable, both in live deployment, so we can update the game without needing to patch, which is a huge service win, but also in development, because we can add gameplay without having to go through a build. You can just edit a script file, hit save, and it is live in the game instantly, which increases your iteration time as a designer dramatically. And we all know that you find the fun by iterating. The more times you hit save on the script, the more fun the game is going to get. So how does that work? Those JSON tables end up starting out as what we call templates. Templates are like cookie cutters, right? They are the shape of what we might spawn inside the game. They control the basic appearance. They have a set of stat fields on them, and they can have scripts attached to them using a component model. You stamp out cookies, individual things, from a template. So you spawn an individual instance of a tree, and it's going to get a copy of the appearance information, a copy of the stats, and a copy of the scripts. Why a copy? Because every single one of those things is runtime modifiable. We are able to achieve efficiencies by referencing back to the template if the value hasn't changed. But as more of it changes, gradually the object acquires a slightly heavier memory footprint. When we attach a script to an object, what we're actually doing is attaching a collection of event handlers. Our game doesn't have a core loop. You can't really build MMO scale with a core loop. If you have to go through and visit everything and tick everything, you'll never achieve the kind of performance level that you need. So instead, our core loop that exists on the server is really an event dispatcher. And it just runs as fast as it can. And it sends events around. Events might come from a client, like a player saying, move north. Events might come from the web, like the auth system saying a player has connected. Events might come from physics. A laser bolt just hit you. And the events might come from other scripts. We actually allow our designers to create their own new events on the fly in the scripting language so that they can create entire systems. But a system for us really means a set of scripts that knows how to talk to the other scripts in its system. Because everything is handled via messaging. Everything is just events flying around. A given script can extend the data structure of an object via adding properties. Those properties will only be present while the script is attached. So let's say I have made a food object. The food value of that object will be a property in the script file. And it's going to assume that the player has some sort of stomach property in the I can eat things script that is attached to the player. It can have triggers, which is our term for the event handlers. These are the messages that it can receive when it is told that something has happened to it. And of course, it can have a function library. Everything in the game is handled via messaging things around. And the beauty of that, not only can we hot reload it, it's fast to iterate, et cetera, if one script has a bug in it, it's just running in its own little thread process, and it it can die and leave the entire rest of the game unaffected. Right? TypeScript can never crash your game. We can automatically surface errors. We can do runaway loop detection or overly heavy CPU usage. We can detect those kinds of things, automatically disable that script from running throughout the game service, and so on. So it gives us a much higher level of reliability, right? Because our goal with an MMO service is to keep it up at the highest reliability we can. These scripts can even set up their own local ticks by messaging themselves if they want to. Everything in the game works this way. When I pull the trigger on my laser blaster and send a physics projectile moving across the landscape to hit some kind of weird, fuzzy purple spider dragon out there, all of that is happening this way. It looks like this. Spawned is an example of a trigger event that is already present in the game system as a platform capability that the main Unity server fires out on every object the moment that it is first instantiated. In this case, this is a tree or a plant. And so the minute that it is born, it says, have I started growing yet? How tall am I? Let me set myself as a height between this possible birth height and this possible birth height. And then let me send myself a message after an interval. And this interval, this tick, is actually fuzzed. You can see this tick fuzz variable there towards the end. That is because in a system of this scale, we never want to have regular ticks so that all of the 20,000 trees process in the same server frame. That is a recipe for periodic hitching lag. So instead, by randomizing the callback frame for every single message that is sent, you essentially amortize the cost of these giant systems and smooth it all out stochastically. It sends the event, and as you can see, you can send arbitrary parameters along with the grow tick event. And down here, we can then handle that and detect things like, oh, am I at the next stage of growth? Do I need to change my art? We have the ability to drive from the server everything about the appearance, every single shader parameter. All of those kinds of things can be driven from scripting from the server so that we can modify all of the objects dynamically on the fly. What does all of this add up to? It adds up to a world in which you can melt rock into lava or fire a heat beam at sand and it turns to glass. And when the lava congeals, you might have turned chalk back into marble. It adds up to players freezing a path across a lake and playing, ice skating on top of it. Or vaporizing the lake and watching it float away. Chemical reactions between different materials can actually erode the landscape and add detail that our artists could never afford to actually put in by hand. All of our rivers automatically get properly eroded river banks and silt forming in the puddles and all of that kind of thing. It just shows up. And of course, really fun stuff like collapsing the roof of a cave onto your enemies and crushing them under 10 times of rock. It also buys us the ability for players to modify this environment because all of this is fully persistent. We track the persistence of the environment per server, and we also maintain a centralized service for things that need to move between the different planets or parts of the galaxy. By allowing players to engage in voxel building rather than building just with prefab props, we can economize on the bandwidth because letting them do voxel building is covered by the transmission of CASIM data rather than the much heavier objects. This just enables players to have completely fresh and new experiences that just haven't been available in a game before, right? Fly through a nebula and then fire a plasma bolt into it and watch it explode and set fire to all the space spiders or whatever is living in there. Hollow out an entire mountain to use as your base, but oops, you delved too deep, the mountain fell on you. Because we actually simulate gravity and arches and adhesion and all of the rest. So then the next obvious question, how do you draw that? I won't lie, it's been really, really hard, right? Like our water alone is a research project. Most video games can just get away with a flat sheet of water and maybe a waterfall particle generator or two, right? We have to handle water that can be both at the same time in a single connected body, right? That has turned out to be a very real rendering challenge for us. We start by using a standard surface nets algorithm, okay? It's one of the standard voxel rendering techniques. Even though our system is not technically voxels, voxels are on-off. In the case of our agents, we actually know the quantity per cell, which we can provide as input into the surface net data, which enables us to build a much more detailed mesh than we would be able to otherwise. And then a very robust shader system sits on top of that, okay, with the capability for distinct textures for the upper surface, the side surface, the underneath surface, grass cluttering systems. We update only the chunks that have changed recently. Chunks are blocks of 16 meters cubed. And of course, all of the textures that you see on here, they're probably actually only sourced from maybe 2 or 3 textures, because the parameters in the shader are enough that we're able to get away with about 10 terrain textures for all of the terrains on the map, even though there's over 120 different materials in the terrain system now. Because, you know, with a properly written shader, you can change the heck out of what it looks like. So all of that ends up turning into something like this. We have to achieve really, really high performance with this, right? So we are leaning very heavily on burst jobs, and I'll spoil something from the next slide. We render all the terrain and all of the liquids in the game in a single draw call using this shader. And that's thanks to the fact that we're building it on URP and are able to do just a really optimized job of building a special case tool to meet our very specialized needs. Nonetheless, we still have to keep a really close eye on the quantity of dirty chunks that can be modified in the server inside of a short span of time. Because if there's one thing that can affect client performance, it is the meshing of this environment. On the server, we take this data, and every second we mesh 12,000 of these chunks into collision meshes. The client has to do more work because it, of course, has to also do all of the shader rendering and so on. So we only manage 3,000 per second on the client. But all of it comes down to one draw call. And we do that with a mesh cluster implementation that is actually DX11 compliant as opposed to DX12 compliant. So it's a very high performance system that has taken a ton of really custom work. The compute shader, if we weren't doing it this way, it has built into it frustum calling and backface calling and all the rest of that. If we weren't doing it this way, it would be the equivalent of 20,000 draw calls, which by itself would use up 15 milliseconds of our draw rendering time. So that obviously would not work. Now, we only update the state of the simulation down to the client. We do it at a slower rate than 60 FPS. The simulation is running at 10, right, FPS. What we do is we actually have a radial awareness system where you get more frequent updates, 5 frames per second for things that are right in front of you, and less based on distance. To cover that up, we lerp the state of the chunks. They basically morph from one state to the other, which is a performance option that you can choose to toggle on and off in your client options. Then on top of this, we layer things like a clutter system that uses pooling so that we can handle everything from the grass to dust when rock falls to water spray for those waterfalls, all handled via the same system. And then we can make that very procedurally based on lookups into the local temperature and local humidity. All of this is enabled thanks to the URP pipeline. Whoop, went one too far. So I just have a static screenshot here just so I can show off some of what this means. This tunnel was not generated. This was actually a tunnel I dug with the digging tool. I was digging through primarily a layer of shale, which is the stone you can see up here on the left, but I hit bedrock on the bottom. But the water reacts with the shale, turns some of it, when there's enough, it turns it into sand, and that sand, of course, has poor adhesion, so it slumps and falls, which revealed a different kind of rock hidden back there. I'm not even sure what that is back there. And where it spends more time in the water, that sand is gradually eroded into clay, which is the reddish stuff that you see edging the bottom. Looks like I accidentally may have unveiled a gold vein there hidden behind. And of course, you can see moss growing on the walls. That is happening automatically. We take the simulation and we have an LOD system that sits on top of it and looks at the ambient temperature and humidity and feeds that into the shader in order to apply things like ice effects and moss effects and the like on top of the terrain. So all of this detail was added from the simulation on the fly. Similarly, you can see the health of the grass changing as we climb the slope because there are differing levels of temperature and ambient humidity as we work our way up. That dirt texture up there in those embankments and the dirt down here is exactly the same, and it is being handled entirely using the shader differences in order to convey these nuances as you climb these mountains. So we get massive economies from embracing simulation in this way, and it adds detail and variety to the world that, frankly, given today's video game budgets, we couldn't afford to do any other way. All of the objects run a single shader, again, in order to be able to combine draw calls. This shader allows us to have temperature response. If you look at that tree there, you'll see temperature response and humidity response meter by meter of the environment, so we can burn the foliage off of only half the tree and then apply the burn effects to part of the tree. This means that unlike traditional video games, we don't specify biomes. They are an emergent quality of the level of detail of the simulation. For us, biomes are actually a local lookup. We go, oh, well, it's this hot and this wet here. I guess this is a savanna, right? And then that determines whether or not a given species of tree will thrive there or not. Players have the ability to change their environment. They can put down heaters and chillers, build greenhouses, irrigate the desert. So we give them the control over this. They may want to plant forests because they really want to grow mushrooms, and mushrooms need a cooler space, and forests cool the environment down. The same super shader also applies on players because all of this customization allows us to selectively replace the materials, patterns, and textures and colors on up to 4 regions of every object in the world independently on every object. So this gives us all of the character customization and color customization that a modern online game service needs. In the end, we're solving a whole bunch of tough problems here, right? We are trying to build this world that feels alive and responsive, a world that lets players take ownership, shape the environment, a world that lets them resculpt it. At a high-end play, players can actually land on one of these planets, possibly drive some of the creatures extinct, import species from another world, start building their homes, plant a flag, form a government on that planet, set the rules, decide whether they want their planet to be a role-play haven or a wretched hive of scum and villainy. run their own shops in a player-driven economy, set tax rates, because, you know, death and taxes, and ultimately feel like they own their world. This approach and this architecture lets us build an environment that makes handcrafted worlds feel like stage sets, right? One of the highest compliments we got was when a fellow developer friend of mine, the first time he got to go hands-on, he just ran around for 30 minutes, and then he turned to me and he grinned and he said, "It just does what you expect." And there's something magical about that, right? Like, that's the holodeck dream, right? Is things that do what you expect. And we've gotten so used to handcrafting every experience and shaping every single moment that having that brief experience of pouring some water on the ground and actually watching it puddle and then watching the grass get happy, you know, it actually brings a grin to your face when you see it happen, right? We were chasing the impossible when we set out to do this. And yeah, it's taken us 5 years, and we're in pre-alpha now. But it wouldn't be possible if it hadn't been for the advances that have been made in cloud compute, the cost curves that have fallen, even new languages getting invented. And it wouldn't be possible if we weren't built on top of Unity, which has allowed us to selectively pick the parts of the engine that work towards our goals and the parts of the engine that just don't, because they were built for other purposes, right? When you need a power drill, it doesn't matter if the engine's version is a hammer, if you can say, well, I'll build my own drill and not use your hammer. And Unity lets you do that. So we have selectively gone through and leveraged the individual systems that make sense for our purposes. And we've leaned incredibly hard into Burst and Jobs and ECS in order to achieve this kind of scalability. And in those cases where things like our simulation, for example, that need to scale beyond even what ECS can do, Unity lets us do that too, and move it on out into Rust and Cloud GPU and so on, precisely because it is modular. In the end, if there's one thing that computers do really well, it's math, right? It's simulating stuff. In many senses, this kind of game is what computer games are for. Because you can't do this outside of a computer. You can't provide this kind of interactivity. Leaning into this rather than leaning into the handcrafted mode of game development has unlocked for us just an extremely exciting landscape of what games can be and the new kinds of enjoyment and fun that they can provide to players. And ultimately, I probably bored you to death with a whole bunch of stats and algorithms and whatever, but I think it's really important to bear in our minds that we ultimately do this not just because it's cool, but we do it for them. We do it to give fun to them. We do it to make them feel empowered, to let them play with agency. And our way of doing that is to chase after that most alive game and give them the coolest sandbox we possibly can. Thank you. I believe we have some minutes for questions. And there are a couple of, yes, we have a couple of people who can help us with those questions.
Hi, thank you for the for how you said it was really, really impressive. My question is about, you talk about the world, but you didn't talk a lot about the players. Like, How do you handle the players? Are you actually shardless for the player? Are you using multiple server instances and stuff? How many players can gather at the same place, and etc.?
Yeah, so we covered a bunch of that in the talk I did just prior to this one down in the community stage, but I'll repeat some of it. We are a massively multiplayer game. It is a single shardless environment. Each of these simulated zones bubbles up and shuts down on the fly in the cloud. That way we can shut them down if there's no usage. Each one of them is individually MMO capable of hundreds of players, potentially up to 1,000. We are still scaling it. We're in pre-alpha. We're in the midst of that scaling testing right now. Go sign up on starsreach.com, join the Discord. You might be able to get in. We currently are running tests every 2 weeks. We open the servers for a couple of hours, hand everybody all the tools, and say, break it, please. And then we go fix everything the players broke. We are not chasing server meshing and seamless environment. Because frankly, we think it is a fool's errand to do so. The dynamic and pattern that we have seen over a couple of decades of MMOs, and I say this, by the way, is we invented server meshing for Ultima Online, okay? So I get it, I know where it came from, all that. But we don't chase it because it's very clear that MMO populations go through life cycles. Often those life cycles have peaks and then valleys and then a peak again. If you build your map so that it is ever growing like a seamless quilt, you can't get rid of squares in the middle of the quilt when they are obsoleted or nobody wants to go there anymore. And at that point, you are dealing with the hosting cost and the memory. You're creating a lot of empty space in the map that nobody wants to visit. You can't obsolete it out very easily. You can't not run it. If somebody's standing next to, they need to be able to see into it. So you have to incur the cost because of the meshing, right? So we said, why not make it work like the web? Which is something we say to ourselves very often. Game engines should work more like the web, right? And if you were following some of what we do with scripting and some of the other things, you'll see that that's a philosophy of ours. So our zones, which include not just planets, but space zones as well, which, by the way, have all the same functionality, because the only difference between them is the skybox and the gravity variable, okay? Everything else works exactly the same. Not only can they bubble up and down, but they are hyperlinked in a graph, connected by wormholes, landing sequences, and so on. That allows us to add density in the middle of the quilt if we need to. If players strip mine a planet, kill everything, and there's nothing left but bedrock, and then they go, see, I'm never going back again, the wormhole can collapse, and we can delete it off the map. So it gives us a lot of benefits, and some of these benefits extend to the future, because we can do things like, when we give them ownership over a planet, we can allow them to set rules like turning the PvP flag on and off, for example, and have a very bright line boundary as to when you're in one rule set versus another. Because our assets stream down on the fly, we can bound the asset download by zone. All of our assets, they're not baked into the client either. They come down on the fly, fetched off of URLs. That means that eventually zones could have user-uploaded assets or scripts that only run on a given world. Someday I have dreams of being the first truly moddable MMO. So the best way to describe it in some ways is, imagine if everybody networked all the Minecraft servers and gave you hyperlinks between them all, right? Each one is MMO capable. But to the player, this will feel like a single living galaxy. Sorry for the verbose answer, but there's rarely one reason why we made a choice. Hey. Next question.
Hi. Great talk. Thanks for it. If I did get that right, the client or the game is made entirely in Unity using URP and ECS, and the server is TypeScript, Web, Node, a mix of Unity and Node or TypeScript, or how's that set up?
Again, that was the talk earlier. But yes, that's correct. There's actually a series of different things that end up running up in AWS there. We have a zone manager service that acts sort of as a nanny process for everything. We have an auth service running up there as a separate process. We have as many zones as we are running. A given zone consists of a Unity server with currently it's an embedded Node.js. But if we end up deciding to horizontally scale scripting, we can actually pull Node.js out of Unity server and run as many as we need per zone. It is paired with a CASIM process. The CASIM microservice is written in Rust. Unity server is Unity server. Node.js, of course, is Node.js. And then even on top of that, there's a variety of databases and things like that for dealing with. There's a character REST service for global data. There's local persistent stores per zone, and so on. So this is not unusual for an MMO. It's very typical for a given MMO to actually require a whole cluster of different kinds of processes in order to handle all of the different activity. One that we don't have yet, but I'm sure we will, is a user proxy routing service that exists in between client connections and the servers. Typically, you multiplex the client connections in an MMO through those for both security and load balancing reasons. We're not yet at the scale where we need to do that, but it is in our future. So yeah, it's a complex architecture. I'm sure that the talk that I gave previously, it was one done in partnership with AWS. I believe all of these sessions are getting recorded. They certainly filmed that one. So we shared the actual architecture diagram of the servers in the walkthrough there. So I'd encourage you to go look for that recording once Unite makes it available. All right, next.
Igilov, thank you so much for sharing this, especially about the temperature part. A slightly less technical question. Have you guys tried replicating our planet in there? Like building, so we can test things out from like an impact perspective. You guys build incredible living world, right? And there are a lot of like big impact climate change problems that we face. And it seems like there's a dynamic here and mechanic that would allow people to see the world through that temperature perspective. And I was just curious, have you thought about that? And what are your thoughts about this? Yeah.
One of our first tests of this stuff was importing digital elevation map data, which flows directly into the system. So yes, we have imported pieces of the real world into this. But more importantly, you've actually you've uncovered one of our not-so-secret agendas, which is this is a game about handing stewardship of living worlds over to players after they ruined this one. And so,
mic drop.
Yeah, part of our intent is that this game serve as a laboratory for hopefully millions of players to try thousands of times to do better and carry those lessons back here.
Awesome. I'd love to talk about that. Yeah.
Let's see. I see a hand up back there.
Thanks for the talk, like pretty interesting one. So question is like a lot is going through Node.js and not the TypeScript and so on and so forth. And there's a lot of the logic is driven through this. So an example you that show, like tree just schedule its own ticks to grow. So you probably like face the issues with the like something fell off that one of advantage that you use, like Node.js cannot crush your server. So how you detect this stuff? Maybe you can share something about it. Like, so you detect that like this one tree is tough to updating, and how you like just fall back from it, like just start row tree again.
So the event queue is reliable. It doesn't drop messages. I don't know how that works behind the scenes. I didn't engineer it. But messages not only don't drop, they even persist if the server goes down, and it resumes its queue when the server comes back up after a crash. So that event dispatcher system is meant to be fault tolerant. Bear in mind that the typical, in practice, we are able to execute all of the pending scripts. Every given event is usually less than a screen of code. So in practice, we're able to execute all of them well under standard frame time. Each of them takes, microseconds. There's hardly anything to them. Usually they're adding a number, changing a number, and sending another event, and then they're out, right? So the other way I would describe this is that the average server loop is a no-op. Most of the time, the server is idle, right? Because the amount of time actually spent inside the scripts is low, right? The trick is actually working with the system that way. As an anecdote, when people first started working on trying to handle all the trees growing, their first pass at the architecture involved a singleton tree manager that allocated clumps of trees, like, okay, we're going to handle 5,000 on this tick, and before that, then too many pile up, and and it was this huge complex thing with a singleton manager, and they posted up the tech description, and I made them just rip it up and throw it away. And I said, no, make each tree manage itself, but fuzz the ticks. That is the path to getting that kind of scalability, right? Is having lots of really small things that can be gone through very quickly instead of having central managers that attempt to process large amounts of data. That same pattern applies even in the individual scripts that you're writing. So, if a scripter has a for loop that's going to process 1,000 things in their script, they're doing it wrong, right? Like, that is an anti-pattern in a structure like this. Instead, even that ought to amortize doing like 10 at a time and giving itself a callback, right? And amortizing it over a few frames. Or even better, just not process lists of data in a script. Like, you shouldn't be doing that, generally speaking. There are other patterns that you can use. So it does require a mental adjustment. We've found that people who work in UI programming or web programming get it very intuitively. And people who are used to working in core loops in traditional video games often don't. But it's surprising how much performance you can gain back. At a really early test, we had 500 alien critters that we aggroed and made them all chase us around on screen. And we were dealing with high CPU tick. And we could see them all rushing and stuttering at us, and the CPU was starting to go up and all that. And we opened up the script, and I went to the line where the engineer had the callbacks, and I just made them put on every single event callback a plus or minus 500 milliseconds, and CPU usage fell by 90%. So a lot of it is about, it's like that old thing they tell you when you're a carpenter. Work with the grain of the wood. Given technologies and given architectures have, ways that go with the grain. And you have to learn what the good patterns are in order to achieve the scalability.
Thanks a lot.
Yes, we are out of time. We are actually over time. So thank you so much. I believe that there's like a whole happy hour worth of food and drinks and probably a very loud DJ. So please enjoy. Please do check out starsreach.com. You can wish list on Steam, join our Discord, sign up for the pre-alpha testing, and join us on our voyage to make the coolest game ever.